cost. So there is a pressure to have cheaper and cheaper systems, especially for heat pumps that compete against the carbon or gas boilers. In order to reach these lower and lower emission limits, you will need a larger passive filter. The wide bandgap enables to have systems without heat sink up to 1 kilowatt. And this one is exactly the power range of the air conditioners.
This is the podcast for engineers, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. Today, I'm joined by my colleague, Giovanni Parrino, who's in application marketing for HVAC, and we're going to be talking about wide bandgap in HVAC systems. Giovanni, thank you so much for being here.
Thanks, Kelsey, for having me here.
Great. So if you're an avid listener or watcher of our podcast for engineers, you probably know that we've talked about HVAC quite a lot. So we recently had an episode with our colleague Lara, where we talked about smart HVAC. We talk about the connectivity solutions. We talk about commercial HVAC. But today, we want to really focus on the innovation in the market. We see that the market is still innovating. What trends in the industry are really driving this innovation?
Yes, we see three main trends that are shaping the HVAC application. The first one is new emission standards. So we have upcoming regulations that will require to reduce more and more the harmonic limits, and then they will push for a higher power factor in the final applications. The second trend is about efficiency. The system efficiency has to be higher and higher, and there are minimum levels of efficiency required by regulations, not only for the final users to reduce the operating cost or the electricity bill, but also the grid network operators want to reduce the stress on the grid and avoid like blackouts in very hot days, like when there are so many air conditioners.
As we've seen recently in the news.
Exactly,
in Europe,
we saw that one recently in Europe, but we could also see the opposite situations, like for example in cold winter nights when heat pumps will be more and more popular, then there the stress on the grid network could be even higher. Third, it is about increasing the cost pressure on the system cost. So there is a pressure to have cheaper and cheaper systems, especially for heat pumps that compete against the carbon or gas boilers.
Mm-hmm.
And then there is a push to have cheaper systems and reducing the cost of the component, active and passive, and also on the assembly cost.
Okay, so you mentioned power factor, efficiency, and system cost. Is there a way that we can address this in the PFC?
Yes. So the PFC, the power factor correction circuit, really has to be designed to limit the emissions and the harmonics. And here we see a trend, especially for single-phase systems, that is the most popular for air conditioners or residential heat pumps. And here we see the shift from the classic boost converter, that it is the most simple and cost-effective for years topology, that it is not good enough anymore. And the fact is that you will need, in order to reach these lower and lower emission limits, you will need a larger passive filter. And that's why now we are going to a new topology, the Totem pole. And the Totem pole, it is a bit more complex topology, and but has the advantages of reducing the EMC filter size, for example. But IGBTs are still struggling with the higher switching frequency, for example.
Okay, so is this something that wide bandgap could improve?
Yes, so especially Totem pole with GaN amps, you could then increase the switching frequency, and then you strongly reduce the size and the cost of the passive filter, for example. And then in this case, you can combine the reaching of the emission limits with the cost-effective solutions.
Okay. Does wide bandgap open any other possibilities in terms of topology or PFC?
Yes, if we talk about the three-phase systems that are more for commercial or larger heat pumps, so then there we also see a topology change. We started from the passive PFC with diodes, that was the simplest ever, and now that they are needed the active PFC topology, and the most popular ones are two: the six-pack, and usually you do with IGBTs or even better with silicon carbide. And this is because you have then higher power density. You can reach up to 20 kilowatt with a molded module, or you can have the Vienna PFC rectifier. The Vienna PFC rectifier, again, it is more complex but reduces the passive filter part. And again, here the IGBT shows their own limits, especially because you need 6 discrete devices.
Can you then swap the IGBTs then for silicon carbide or GaN in Vienna rectifiers?
Yes, the GaN will be a game changer in this case, because then you can replace 2 discrete IGBTs with one single GaN BDS. BDS stands for bidirectional switch. So then with a single switch and a single package, then you can make the same. So you can reach the same performance or even higher than 2 discrete IGBTs. And this one, again, will have a positive effect on the system performance and on the cost.
Okay, and with fewer components, that's nice always.
Exactly, fewer components, easier layout, and also easier driving thanks to our enhancement mode GaN HAMs, yes.
Okay, so we talked about PFC, but what about the inverter side?
Yes, so also for inverters, we have to differentiate between one phase and three phase. But the important thing is that especially for the single phase, again for air conditioners, the wide bandgap enables to have systems without heat sink up to 1 kilowatt. And this one is exactly the power range of the air conditioners. So then here we can have, if we replace IGBT with GaN, you can remove the heat sink, and then also can really strongly reduce the assembly efforts and the assembly cost. And this one really addresses the trend that we said before on the price pressure, and while increasing again also the efficiency, especially at the light and medium load.
Okay, do we offer our customers anything to get them started?
Yes, we also have. We also can demonstrate that. We have an evaluation board with 1 kilowatt that does not need force the airflow and does not need the heat sink, of course, according to the different application conditions. Then for three-phase PFC, in this case, silicon carbide helps. And again, we can use the B6 topology, and then here we can use our molded modules and then reach again up to 20 kilowatt electric power for the with a molded module. And then here you strongly reduce the size, you improve the assembly, and then you will have an advantage at system level.
Okay, so we've been singing the praises of wide bandgap technology today, talking about, I think, game changer was your word that you used, but are IGBTs not suitable for HVAC anymore?
It is not fully correct, because IGBTs still have their own niche, in the sense that they are still the most popular technology, and they are more or less they can be considered the cheapest at component level, but maybe they will not be future-proof, and they will not be maybe convenient at system level. So depends on the customers, depends on the project specifications. All the three technologies will coexist together, and then we can support our customers, as we have a large portfolio that includes all the three technologies and different packages. Then there we can recommend our customers the best technologies for their needs.
Okay, great. Giovanni, I think that wraps it up. And I really thank you again for being here. Appreciate it.
Thank you, Kelsey.
Yeah, and I know we have a few other things coming up on this topic, wide bandgap and HVAC, an upcoming webinar. So if it is published before or after this podcast episode, no matter, I'll link everything in the description below, as well as the link to that evaluation board you mentioned. Thanks again, and thank you to our listeners. If you're interested in what's going on in the semiconductor industry, please stay tuned for more episodes.